Hi, everyone. Thank you for attending this week's Pelton Chemistry webinar. I'm Bo Xiang from UC San Diego, and I will be the host. Today's speaker is Professor Matthew Pelton from University of Maryland. And before we start, I would like to introduce the schedule and mechanisms of this webinar series. So our Pelton Chemistry webinars will be held every Wednesday at 9 a.m. Pacific Standard Time. For each talk, you must register using the link we provided here or the link we included in our reminder emails we send out every week. You can also follow our social media on Twitter and Facebook to track the updated status of our webinar series. Also, we created a Facebook group called Pelton Chemistry Online Community, where you can share recent findings, research papers, and other related topics. You are most welcome to join us if you haven't done that. If you have missed the live or would like to rewatch it, feel free to go to our YouTube video channel called Pelton Chemistry Webinars, and don't forget to subscribe. And finally, I would like to introduce the webinar mechanisms for new attendees. During the talk, you can use the raise hand button to ask questions, and I will interrupt our speaker at appropriate places and enable your audio for you to talk. You can also use the chat button to discuss with everyone for the webinar. And for Q&A, you can write down your questions, which will be raised during the presentation. For the questions that are not addressed due to a time limit, we'll collect them and send them to the speaker later. You may find the responses from our social media. Okay, now let's move on to today's webinar. Our speaker today is Professor Matthew Pelton from University of Maryland, Baltimore County. Professor Pelton obtained his bachelor's degree in University of Toronto, and after that, he went to Stanford University for his PhD career. After grad school, he had a brief postdoc appointment at Royal Institute of Technology in Sweden, and a longer postdoc at University of Chicago. He was a scientist in the Center for Nanoscale Materials at Argonne National Laboratory before joining the physics department of UMBC. And his research in Maryland focuses on understanding and controlling what happened when light hit nanoparticles. And he also uses ultra-fast laser pulses and optical microscope to study the processes where the nanoparticle absorb and transform the energy from the incoming light. And today, Professor Pelton will give us a talk entitled Room Temperature Strong Coupling between Plasmonic Nanocavities and quantum dots. With all the introduction, let's move the stage to Professor Pelton. Professor, you may now share your screen. And I will stop share. Yeah.
All right. Do you all see my screen now? Oh, there I am. All right. Well, thank you for the introduction, and I also would like to thank you all for coming, and thank the organizers for inviting me to give a talk in this webinar series. I've been attending some of these talks since this series started back in April, and it's been a really great way to stay connected with the community now that we can't actually meet with each other in person. I haven't been able to attend as many of them live as I'd like to, so I'd also like to thank the organizers for putting these up on YouTube so we can watch them afterwards. It's really been a very impressive group of speakers, and I'm honored to be part of this. So I changed my title very slightly from the one that you just saw a minute ago. I put the word single in there because in some sense that's more important for what I'll talk about today than the fact that we're using quantum dots. Towards the end of the talk, I'll actually talk about a number of collaborative projects that don't actually involve quantum dots at all, but the coupling and strong coupling to all sorts of other systems but with a common factor that these are all involving plasmonic nanostructures, which are enabling us to get strong coupling at the single particle level, in many cases at room temperature. So I feel like I don't need to give too much of an introduction to this audience to strong coupling and fluoritons in general, but just to put things in a little bit of a historical context, I guess.
Professor,
yeah,
sorry to interrupt. I think
okay.
You might not in the presentation mode.
Oh, are you seeing the wrong
we
screen?
can see the next slide.
Okay, let me see if I can, you're seeing the wrong screen.
Yeah, now it's good.
Is that better?
Yeah,
right.
yeah.
Sorry about that.
Thanks, no problem.
So so I was saying the field of plasmonics, or at least the modern field of plasmonics, basically started with the observation of surface-enhanced optical processes. With first the observation of surface-enhanced Raman scattering back in the 1970s, which people rather quickly realized was primarily due to the localization of light in nanometer scale volumes when plasmons are excited in metal nanostructures. And if these can give these very large enhancements of Raman scattering signals, they can also enhance other optical processes, including spontaneous emission. So the chemists that were working on this first observed this just a couple of years after SIRS, described this primarily in an energy transfer picture, where the emitter transfers its energy to the plasmon, which can then radiate to the far field. A little time later, the electrical engineers got into it from primarily the scanning near-field optical microscopy community, and described things in their language of optical antennas, where the antenna overcomes the impedance mismatch and allows the emitter to efficiently broadcast its radiation to the far field. And these, of course, are equivalent descriptions, and they're also equivalent to the cavity quantum electrodynamics work that was going on in parallel at the same time. So independently, other physicists were putting atoms inside optical cavities and modifying their spontaneous emission rate by changing the available density of electromagnetic modes for them to radiate into. And what's going on with the spontaneous emission modification with plasmons is the same cavity QED. But now the cavity is this plasmonic resonator, which can confine fields to subdiffraction limited volumes. So in the language of cavity QED, the enhancement that you got for the spontaneous emission rate, the rate of emission into these cavity modes compared to the free space emission rate, was proportional to the quality factor of the cavity, the photon lifetime, inversely proportional to the mode volume, how tightly confined the light is. And ordinary photonic cavities are limited by the diffraction limit to have a mode volume of about half a wavelength on the side. So if we carry this idea over to these plasmonic cavities, and keeping in mind that this is, we have to be careful about things like defining mode volumes for open cavities, and there's been a lot of very good talks in this series about the proper theory for describing quantum electrodynamics in these sort of systems. But I'm not going to get, my theory is not nearly as sophisticated as all of that. And just as a sort of a heuristic, we can still think of the mode volume, the confinement volume around these plasmonic nanocavities as being no longer restricted by diffraction, because you're coupling to those material excitations. And now you can get Purcell factors that are much higher than you can get in photonic cavities, even though the quality factor of these plasmonic cavities is quite low. Photon or plasmon lifetimes inside these cavities are in the 10 to 100 femtosecond ranges, given quality factors on the order of 10. But nonetheless, the highest Purcell factors people have observed are in plasmonic systems. So that did lead to the idea that these systems could also be used for strong coupling cavity QED, for formation of polaritons, hybrid plasmon exciton modes or plasmon emitter modes in these systems. And there really is a sort of formal mapping between the cavity QED and this plasmonic cavity QED. In the simplest model, the James Cummings Hamiltonian that's used for cavity QED, where you couple a two-level system to photons in the single mode of a cavity, you can replace the bosonic field of those photons with the bosonic field of the plasmons inside the cavity. And this is really just to show some of the level of theory that I'm going to use to either make predictions or describe our experimental results here. In some cases, with Stephen Gray, who I think is listening right now, we did do fully quantum mechanical calculations in the Heisenberg-Langevin picture, the master equation picture, using Lindblad operators to describe the damping that's not incorporated in the James Cummings model. But basically, for everything that you are going to get with plasmonics, especially at room temperature, this all reduces to a semi-classical situation, that you don't have to actually quantize the plasmon field. You can treat it classically using the Maxwell block equations, keeping the emitter, the exciton, or whatever system you're looking at as your two-level system. And if you're interested only in the linear response of these systems, right, relatively weak excitation intensity, the system stays in its ground state, then this reduces further to a fully classical pair of coupled harmonic oscillators, where each oscillator represents the dipole moment of, say, the plasmon, dipole moment of the exciton. They're coupled together through the near field of the plasmon. And this simple pair of classical coupled harmonic oscillators reproduces quantitatively the linear spectra that you have in these systems. And again, this is not an exact quantitative theory, but it's good enough to explain most of what we can actually see experimentally, and it also gives us a good handle on what's going on in these systems, as we change these parameters. So here I've just plotted, using sort of typical parameters for plasmon line widths, quantum line widths, and oscillator strengths at room temperature, what the scattering spectrum here on the left and the photoluminescence spectrum on the right would look like in these systems as you increase the strength of the coupling between the two of them. And we go from the, let's say, having the same photoluminescence and scattering spectra of the isolated metal nanostructure and quantum dot, to the strong coupling regime where we're forming polaritons in both the scattering and the luminescence spectra represent the splitting into these hybrid polaritonic modes. And this strong coupling criterion, well, within some factors of 2 that you may or may not agree with, tells you when you are forming these hybrid modes, when you get Rabi oscillations that coherently transfer energy back and forth between the exciton and the plasmon. But there's also an interesting regime in between, where I think most of you are familiar with this other figure of merit, which is the cooperativity. There's a different combination of the coupling strength compared to the cavity and emitter line widths. And in the plasmonic systems, you can get a induced transparency effect. You get 2 maxima in the scattering spectra, even when you only have 1 in the photoluminescence spectra, because of a destructive interference. So it's described as sometimes as a phono kind of interference between the quantum dot and plasmon dipole, but I prefer to describe it as a induced transparency or exciton induced transparency that cancels out the dipole moment of the plasmon at the exciton transition frequency. And both of these have the potential to enable interesting applications. The strong coupling regime is really the focus of this series, and I think people are familiar with the chemical and quantum information potential applications there, but there are also strong nonlinearities that show up in this exciton-induced transparency regime, which I'll talk about a little bit later, the potential applications in classical information processing and maybe even quantum information processing. But in both cases, what you need to do in order to get higher cooperativity or strong coupling is to have a coupling strength that's large compared to the line widths in the system, the cavity line width or plasmon line width and the emitter line width. And for photonic cavities, the coupling strength is strictly limited by the diffraction limit. The coupling strength scales inversely with the square root of the volume. So the smallest mode volume that you can get is limited by diffraction. So the only thing that you can do further to get strong coupling is to make the line widths of the system narrow. Making the cavity line width narrow is not a problem. You can make very high quality photonic-crystal cavities, for example, that have nearly diffraction limited mode volumes. But the emitter line width is going to be limited by thermal dephasing. So, especially in a solid state system. So your choices are either to have a completely isolated system, like a single atom or a cold gas of atoms, or to take your solid state system and cool it down to cryogenic temperatures to get the line width to be small enough that you can resolve the two polarotonic peaks. But in plasmonic cavities, you're no longer limited by this diffraction limit. Their plasmon line width is very broad, the lifetime is very short, to the point where even room temperature thermal dephasing is smaller than the plasmon lifetime. So you have to get an even stronger coupling strength in order to reach the strong coupling regime. But you're no longer limited by the diffraction limit. You can get down to the single nanometer dimensions for your mode volume and have the potential to really do this using single emitters at room temperature. So I should emphasize that these equations don't have the square root of n factor that you have when you have multiple emitters coherently coupling to the same cavity mode. And our goal really is to reach this at the single emitter level, which enables quantum information nonlinearities, the other very strong nonlinearities that are going to be diluted when you have multiple emitters coupled. So our goal is to make the mode volume as small as we possibly can. And I think it's been known, again, since the early days of plasmonics, since the surface enhanced spectroscopy days, that the smallest mode volumes, the greatest localization of light that you can get comes when you couple plasmons together. So if you take two metal nanoparticles and bring them close together, the plasmon oscillations in the two are going to couple electrostatically through the Coulomb interaction. Charge is going to be localized at the surfaces close to the gap between the particles, and the field is going to be localized in the gap much more strongly than it will be localized by a particle by itself. And a similar configuration that's somewhat easier to realize experimentally, instead of bringing two particles together, you can bring one particle close to a metal film. And in a sort of hand-waving way, you can think of the dipole of the plasmon in the particle interacting with its image dipole inside the metal field, and again, producing a gap-plasmon resonance localized within this gap that can be down to really single nanometer type of volumes. And these are the sort of target spacings that we're looking for in our system, down about a nanometer or so. The smaller the better. If you make it much smaller than that, then you start to get issues with charge transfer and electron tunneling and Landau damping. So we need a little bit of space to keep the systems isolated from each other. And we use quantum dots in this system. Other people have used single molecules in a very similar configuration to reach the strong coupling regime. Molecules are smaller than quantum dots, so you do lose a little bit in terms of how small your mode volume is when you use quantum dots. And here I'm talking about colloidal quantum dots, semiconductor nanocrystals, particular cadmium selenide, zinc sulfide, core shell nanocrystals. There are a few nanometers in diameter, which limits the spacing, but what you get in return is a stronger dipole moment, a transition dipole moment inside the quantum dot compared to a single molecule. You get relatively high photostability, so they're less subject to photo bleaching or photo damage from these very tightly confined fields. The molecules are, and also we can just tune the transition frequency in these quantum dots by changing their diameter to match the resonance frequency of this gap plasmon, so that we can get the detuning down to zero and the strongest coupling possible between the two of them. So in our first demonstration, we did this sort of in a random kind of way in collaboration with a group of Mary Christine Danielle at UMBC, where we basically decorated the surface of gold particles with a small number of quantum dots. We functionalized the surface of the gold particles with one kind of molecule and the quantum dots with a complementary molecule, use a linking reaction to get just a few of them onto the surface of each quantum dot. So you can see in this electron microscope picture here, and then take those nanoparticle assemblies, put them down onto a silver film, and hope that we're going to have a few of them that landed so that there's a single quantum dot in the gap between the metal particle and the metal film. Most of the time, quantum dot's not in the right place. So if a quantum dot's nearby the gap, we can still get a strong reduction in its lifetime a strong per cell enhancement, but the scattering spectrum here in blue, photoluminescence spectrum here in green are largely unmodified compared to their the spectra for the isolated particles. But every now and then, we're lucky, and there's a quantum dot in the right place, and we can get the strong modification of these spectra. So this is showing the example of the exciton induced transparency, the high cooperativity regime, where there's a pronounced dip in the scattering spectrum that coincides with a peak in the emission spectrum from the quantum dot. And if you have a patient graduate student who's willing to hunt around long enough, you will eventually find a few cases where you were really into the strong coupling regime, where there's a splitting of both the scattering and the photoluminescence spectra into the hybrid polaritonic modes. So, one obvious question is, why do we see different coupling strengths in different configurations, right? And why is it only a couple of % of the time that we get into the strong coupling regime, and only a little bit more often that we get into the intermediate coupling or induced transparency regime? So to understand that qualitatively, we turned to finite element calculations. So these don't reproduce our experimental spectra quantitatively, but they do show the same trends. And the important thing here is that if we take a sphere, we put a quantum dot close to the gap, we really don't see any significant change in the scattering spectrum. And even if we do put the quantum dot right in the right location between a gold sphere and the silver surface, we saw only a relatively modest induced transparency, and we certainly do not get into the strong coupling regime. And the reason for this, of course, is that those gold particles aren't really spheres, right? If you synthesize or purchase gold nanospheres, most of the time you're not actually getting spherical particles, you're getting these highly faceted particles like you saw in that electron microscope image. They're a cubic lattice and they don't like to be round. So if we just put some facets onto the sphere and put the quantum dot either along the edge of a facet or at the vertex of multiple facets, we can see that this coupling gets stronger and stronger, and we get deeply into the high cooperativity and all the way into the strong coupling regime here. So what we're seeing is that the coupling strength is really very sensitive to the detailed nanometer scale structure of this, plasmonic nanocavity that we're fabricating. And in this experiment, we don't have a lot of control over that kind of nanometer scale structure. We just have to look around and hope that we can find the ones that we're looking for. So to make things a little more controlled, or I should say, I guess a lot more controlled, we worked with Marcus Raschke at the University of Colorado and essentially replaced the gold particle with a scanning probe tip, a near-field scanning optical microscope tip, also made out of gold and tapered down to a nanometer scale point at its end. So this tip now we can scan it around the surface, find the quantum dot, and position it directly on top of the quantum dot, and do this over and over again with different quantum dots on the sample. So you can see that we go from just having the emission spectrum of the isolated quantum dot. When the tip comes nearby, the emission gets stronger. We're seeing the Purcell enhancement when we're still in the weak coupling regime. And when the tip is located right on top of the quantum dot, the photoluminescence spectrum splits into two clearly resolved peaks, bringing us solidly into the strong coupling regime. And now, like I said, we can do this over and over again. We can do this for one dot, move over to another dot, measure many dots this way. Tip is always the same, but the quantum dots are all slightly different. They have slightly different size and shape, so they have slightly different transition energies. And we map out the detuning between the quantum dot and the tip and see a sort of characteristic anti-crossing behavior that is really defining feature of these plasmon exciton polaritons. And there's some dispersion, some width to this anti-crossing behavior because the quantum dots also, in this case, have a random orientation, which means that their dipole moments are oriented in different directions compared to the polarization of this gap-plasmon mode, which is normal to the metal surface. So that that misorientation between the two of them affects their coupling strength. But within that range, we still, get the anti-crossing that we expect. And we can also, move the tip relative to one quantum dot. So we can change the coupling strength by scanning the tip either laterally or vertically, bringing it from away, further away from the quantum dot on the sample to right on top of the quantum dot, and seeing this single peak split into two and then go back down to one, or sit on top of the quantum dot. And as the tip is moved up vertically, the split peak merges into one peak. So the coupling strength dies off on just a couple of nanometer scale in the vertical direction, whereas on the horizontal direction, you can scan the tip over about 10 nanometers before you start to lose this strong coupling. And we can see why this happens, again, turning to finite element calculations. If you take the tip that's already sitting on top of the quantum dot and you move it away, then what's happening is just the cavity is getting bigger and bigger. The move volume is getting larger, the coupling strength dies down, and that happens on dimensions comparable to the size of the mode volume of the cavity in the first place. So your coupling factor dies off in a couple of nanometers. If you're scanning laterally, on the other hand, if you move over but are still in contact with the dot, you haven't made your mode a lot larger, you've just changed the mode that you have. You've reconfigured the localized field inside this cavity. The mode volume is slightly larger, but not significantly larger in this case. It's only when the distance from the quantum dot is comparable to the radius of curvature of this tip itself that you start to get back into the weak coupling regime. So from these calculations, we can reproduce the experimental trends that we see, and it shows that this is a good tool for understanding quantitatively what's going on in these plasmonic nanocavities, that we can dynamically tune these things and control their dimensions on the sub-nanometer scale, and really get single quantum dot, single nanometer resolution in these nanocavity experiments.
Professor, we have one question here.
Sure.
Okay. Yeah, where you can.
Hey, Matt, I just have one quick question. So it seems the tip is tilted. So is there a dependence on the tip angle, or is it important to have the tip to be tilted?
It is important. It's not, the tip angle is not something that's controlled dynamically in the experiment. So the tip is fixed at about a 30-degree angle, I think, 37-degree angle to the surface. And the reason for that actually is because that gives you better excitation of this vertically polarized gap-plasmon mode. So, typically people tend to have the tip located, oriented perpendicular to the surface. And in that case, you're coupling to plasmons that can propagate along the length of the tip. But when you tilt the tip relative to the surface, then you're coupling to plasmons that are confined vertically along the dimensions of the tip. So the tip really is looking much more like a nanoparticle here. That you're really, the far end of the tip really doesn't matter for these localized plasmons that you get here. So Marcus Rash's group showed a few years ago that this tilted configuration gave you much stronger localized fields and stronger coupling than a vertical tip does.
I see. Thank you.
Sure. That's a good question. It was a relatively simple experimental change that actually is one of the things that enabled us to get these very strong coupling strengths that we did. And I should say we do that coupling strength calculation both for the experimental data and for these theory calculations by fitting the line shapes that we have to our coupled oscillator model. So we're not just looking at how far apart the peaks are, because that can be misleading, especially in this induced transparency regime, but by doing a line shape analysis. And so for our two cases, the first one of our nanoparticle above the surface and then our scanning probe tip above the surface, we are solidly into the strong coupling regime. and into this high cooperativity regime, which enables the quantum information applications. And since people have done different kinds of analysis in the literature, we decided to go back and reanalyze previously published data. There have been other papers since then, but you know, not to go into the details, everything is pretty close to the strong coupling regime, where it, getting into the high cooperativity regime actually turns out to be more challenging. But I guess the point is, we think our numbers are pretty good. But you know, they're hard to get. The putting the nanoparticles down randomly is obviously not the way that you're going to get towards devices or even really reproducible experimental studies. And the scanning probe tip gives you quite a bit of reproducibility, but it's one particle at a time. And again, this is not a path towards making functional devices, you know, using these things in applications. So we're working now still with a group of Mary Christine Danielle on trying to use these bottom-up the chemical assembly techniques that we have, but to modify them to give high yield synthesis of quantum dots in the gap between pairs of nanoparticles. So for either gold bipyramids or gold nanorods, both of which are well-established syntheses, we're going to try to selectively functionalize the ends of these things, link them to the quantum dots in such a way that we end up with a high yield of free particle chains, so the metal nanoparticle, quantum dot, and metal nanoparticle, the quantum dot located right where this field is going to be the highest between the two of them, and really have, you know, macroscopic number of these strongly coupled systems that we can then study further or incorporate into devices. On the right-hand side here is just showing some pictures from a while ago towards this, where we're coupling metal spheres to metal nanorods, and you can see we have some control over where the spheres go, but we've got a little ways to go yet in putting them exactly onto the ends of the rods. So that's sort of the ongoing work there. I've been talking about, you know, incorporating these things in devices, using them in applications, but I haven't really talked about what those applications might be. So one of the main things I think that's going to be interesting to look at with these systems going forward is not just their linear optical properties, but their nonlinear optical properties. And the first step towards that, with a group of Haik Hartunian at Emory University, we started looking at maybe the simplest nonlinear optical process that you can have, which is second harmonic generation. So here we are using these gold nanorods. Instead of coupling the quantum dots, we coupled to a monolayer of tungsten diselenide. These transition middle dipole collagenide, especially tungsten diselenide, have narrow line width and excitons that are stable at room temperature and have very large oscillator strengths. And the gold nanorods give you fields in the vertical direction normal to the surface that line up with the transition dipole moment of those excitons. So this kind of configuration has been used several times already to show strong coupling at the single particle level. The single particle here meaning a single metal nanoparticle level to excitons inside TMDs. And the goal here was to go one step further and look not just at the linear spectra, the scattering or photoluminescent spectra, but to look at the second harmonic spectrum, the nonlinear spectrum of this. So what they do basically is take an excitation laser and tune it across the plasmon and exciton frequencies here. And what we're seeing in these graphs is the intensity of the second harmonic signal that comes out as the excitation laser is tuned across this system. You can see there are clearly two peaks in the second harmonic excitation spectrum. So the second harmonic is coming not from the isolated exciton or plasmons, but from these hybrid polaritons inside the system. And we can understand this again in a classical sense. The strong coupling is rarely a quantum mechanical phenomenon. It's really something that you can understand very well classically. So the simplest way to do it is just to take our coupled harmonic oscillator model that we already had and just add second order nonlinear terms, add an anharmonic term to each the oscillators. So now we have coupled anharmonic oscillators, and the usual kind of perturbation analysis gives us the second harmonic intensity as a function of the fundamental frequency. You can see that we reproduce pretty well the experimental spectrum that were measured. And we get the same phenomena for more sophisticated calculations. So Maxim Sukharev, Arizona State University, did fully hydrodynamic models for the nonlinearities of the metal nanoparticles, and either incorporated chi2 nonlinearity for the TMDs or not, and you could show the same spectra that we get experimentally in these fully numerical finite difference time domain simulations. So this is experimentally a first step in demonstrating the nonlinear optical properties of these coupled systems. There's maybe nothing terribly surprising going on here. The demonstration that the flaretons are the nonlinear elements instead of the excitons. I think there is a raised hand, right?
Yes. So there's one question from Howell.
Hello. I have a question. What is the actual role of the strong coupling in the enhancement of the nonlinearity? Is it just to change the energy levels of the states that are associated with the chi2 process and just induced resonances, appropriate resonances, or is there something deeper than that?
Yeah, so at this point, I'd say it is what you're saying. So I don't think that there's anything more going on than just changing the energy levels that are involved in the second harmonic process. It's not easy experimentally to measure absolute intensities to calibrate the efficiencies of these processes, but at least in the calculations, we don't see anything qualitatively different going on apart from the splitting into the two different levels.
Okay, sorry, one more question, I guess.
Yeah.
In these systems, I mean, presumably you have many excitons. This is in the collective strong coupling regime, right? Because your nanoparticle is big, and then there are several excitonic transitions that you're coupling to. Am I correct? Or
yeah, I mean, yes, it's hard to count how many excitons are involved in the TMDs. So the excitons are delocalized throughout the TMD, right? So it is a collective coupling of excitons in the tungsten diselenide to the plasmon. If you want to get an estimate of how many excitons are involved, you can compare the coherence area of the excitons to the mode volume of the plasmon, and the mode volume is much smaller than that coherence area. Or you could compare the Bohr radius, the Bohr diameter in plane of the excitons to the mode volume, and you get a single digit kind of number, not one, but just a few excitons, if you just want to say how many Bohr radii are there within the area of the localized fields. But it's not a single. This is not a single exciton in the sense that the quantum dot is really truly a single exciton system.
Okay, so I guess the last question I would ask is, I mean, normally in the strong coupling regime, we worry a lot about basically relaxation to the dark states that can destroy all the effects of the strong coupling. And I guess in your case, you need to worry about relaxation to these dark states due to the effect that the strong coupling is collective rather than single exciton.
Yeah, so I mean, one thing to say is that we don't see any excitation of the dark state in the second harmonic spectrum. So the Maxim has done calculations where if you have a really macroscopic system, you start to see a third peak show up in the spectrum,
I see.
At that dark state energy. So I'm not saying it's not there. I mean, it is there. But of course, if you want to count the number of excitons, n is 3, 4, something like that. So the dark state reservoir is small. I guess. That's one way of putting it. Right? Okay. But it is there. Yeah, this is important, and this is where we are now. And we would very much like to move this into the single exciton regime, so that there is no dark state reservoir, so that we're really looking at these nonlinear properties at the single exciton level.
Thank you very much. That answers my question.
And that actually leads in nicely to what I was going to say next, because doing this at the single exciton level also leads to more exotic or to nonlinearities that really do take advantage of either the induced transparency or the strong coupling. And the quantum information applications that people are looking at, photon state transfer coupling, single photons to single spins, or having photon-photon interactions at the single photon level, have all employed these sorts of phenomena in the cryogenic regime, say in epitaxial quantum dots and single photon cavities, photonic-crystal cavities. We think that similar ideas can let us get very strong nonlinearities in these coupled exciton plasmon regimes. But the being able to do this at very low powers and having very strong nonlinearities nonetheless is really enabled when we can get down to the single exciton regime. So these calculations from a while ago, Stephen will answer any questions that you have about them. We just were assuming a quantum dot between a pair of metal nanospheres. So the induced transparency we're getting is actually not that great. We could do better than this already experimentally. But if you just shine continuous wave radiation on this coupled system and look at how the scattering spectrum, or in this case, the absorption spectrum, evolves as you turn up the power, you see that this dip, the induced transparency, disappears. And the mechanism is pretty straightforward. You're just saturating the transition of the quantum dot. So its transition dipole moment, when it's saturated, it goes to 0. So it's no longer coupled to the plasmonic system, and this induced transparency is no longer there. But the saturation now, which is a weak nonlinearity in the quantum dot because of its small transition dipole moment, is amplified by about 4 orders of magnitude by coupling to the much larger dipole moment of this plasmonic system. So you can get very large changes in the absorption cross-section at relatively modest optical intensities. These are not maybe the smallest optical intensities, but it's, worth remembering that the footprint of this device is very small, so the actual amount of power that you would have to put in to get this modulation would be in the nanowatt regime. And it would be ultra fast too, because the recovery time of this system is in the picosecond or sub-picosecond regime. So you could have an ultra low power, ultra fast, and really nanometer scale optical modulator where you could control the transmission of light through the system with a very low power control beam. And this would be an important ingredient, in future all optical information processing. We have a ultra small all optical modulator. It could be also used in somewhat more unconventional all optical information processing architectures like neuromorphic computing. So this was a theory paper with Volker Sorger where we showed that the nonlinearity provided by these coupled plasmon exciton systems could in principle be used to provide the nonlinear activation function in an all optical neural network, so that the processing speed, the compute speed in these networks would only be limited by the propagation time of light from the input to the output. So you could really do really small scale neural networks at the speed of light. And I'd say some of the most theoretically interesting nonlinearities that people have been talking about, especially theoretically recently, have become in the ultra-strong coupling regime. But achieving the ultra-strong coupling regime, at optical or near optical frequencies has been relatively challenging, especially if you want to get the amount of material involved to the ultra-strong coupling down to small volumes to enable these nonlinear processes to happen. You can always get stronger coupling by having more material, but then you're going to have to use higher powers to see these nonlinear effects. So towards the goal of really reducing the volume involved in ultra-strong coupling, the work with Sung-Hyun Oh at the University of Minnesota is developed a method for fabricating wafer scale arrays of really nanometer scale coaxial plasmonic cavities. These are basically films of gold that have small rings cut through them, filled up with a dielectric material, in this case silicon dioxide. So these rings are acting like coaxial waveguides with nanometer scale, few nanometer gaps between the metal walls of that waveguide. And the film is not very long, so reflections at the top and bottom surface lead to Fabry-Perot resonances inside these coaxial cavities. And by operating near the cutoff of these coax waveguides, you can get highly uniform fields throughout the entire nanocavity. Right? If you look at it in terms of the effective mode index or the effective mode dielectric constant, these are operating in the epsilon near zero mode, where you get near zero phase shift and uniform fields throughout the entire cavity. So that any material inside the cavity, regardless of where it's located, is going to couple strongly to these localized nanocavity modes. In this case, the system that's coupling is the vibrational modes, the optical phonons inside the silicon dioxide that fills up this cavity. So by designing cavities that have infrared resonances near these optical phonon modes, we are able to get strong coupling and ultra-strong coupling between these optical phonons and the cavity resonances. Cavity resonance frequency can be tuned simply by changing the diameters of those coaxial cavities and swept across this Renstrahlen band between the longitudinal and transverse optical phonons. And you can see that this transmission peak, as it approaches the phonon energies, splits into two peaks with a large splitting that's much larger than the width of this Renstrahlen band, is really representing ultra-strong coupling. And again, not to go into the details of the fitting and the model that were used, but a classical model reproduces, again, the same results as a fully quantum mechanical ultra-strong coupling model in this case. And the anti-crossing curves give you a coupling strength, which is about 25% of the transverse optical phonon frequency itself. So, ultra-strong coupling is, I think, generally held to occur somewhere about 10% of the transition frequency. So we were pretty well into the ultra-strong coupling regime here. I should say here we've moved into the infrared wavelength regime. Right? We're coupling to solid-state phonons in this case, but of course, going back to the sort of original topic of this webinar series of polaritonic chemistry, coupling to vibrational transitions in molecules at infrared frequencies has been, I think, of great interest as a way of modifying the chemical properties of materials. Whether or not that's going to work, certainly an interesting thing to look into. The last thing I'm going to mention here is work with Matthew Sheldon at Texas A&M, where they've made a sort of metamaterial, something very similar to the particle on a metal film that we looked at before, but now with an array of these particles coupled together laterally in a collective resonance that provides highly uniform fields, so that if you put down a material, in this case copper, hydrated copper sulfate, and coat this metamaterial with that molecular material, then you can get coupling across the entire thing. In this case, again, collective coupling to the vibrational modes of that material, and specifically here to the symmetric and anti-symmetric stretching modes of the water in this hydrated copper sulfate. And again, the resonance frequency can be tuned by changing the diameter of these disks. So you can sweep the plasmon resonance frequency across this the vibrational mode frequencies inside this material. And as we do that, we see a splitting of the transmission spectrum or the absorption spectrum as the simultaneously. So if we try to fit this to a 2-oscillator model, we can't reproduce the experimental results, but we can get very good fitting. We have a 3-coupled oscillator model where the 2 are infinitely straightforward. Interestingly, it's inducing an effective interaction between these vibrational modes that were previously uncoupled or very weakly coupled anharmonically within the water molecule. Now, since they both couple to the same plasmonic mode, there's indirect energy exchange between the 2 of them, and maybe with some implications, say, for polaritonic chemistry. So I know the last part of my talk was sort of a little scattershot there. I'm not going to try to summarize everything I have, but just give a last slide on the vision here, at least my vision. I can't speak for all of my collaborators, but I think what I'm trying to aim towards in all of this is achieving these strong coupling effects reliably at room temperature at the single transition level, whether that's an electronic transition inside a semiconductor or a vibrational transition inside the molecule. If we can reliably, reproducibly make systems where we can get that strong coupling at room temperature, then we can enable these low power optical nonlinearities, maybe down to the single photon level, but certainly at low powers to enable classical and maybe quantum information, all optical information processing. And that we can really understand what's going on inside these systems because we're going to be able to investigate them one molecule or one particle at a time. So we have the ability to see what the decoherence pathways are inside these and potentially control those decoherence pathways to increase coherence lifetimes, enable these applications, and more broadly to really understand the energy flow pathways and maybe control the chemical pathways in these strongly coupled systems. So thank you for paying attention, and I guess I'm happy to take more questions.
Okay, thank you, Professor Pelton. So I'll allow people to ask questions. Let's see. Hey, Matt, you can ask questions.
Hi. So throughout the talk, you showed samples that show this EIT and the strong coupling, and you showed some samples that only show one of them and some samples that show none. So there's, as you mentioned, there's a lot of variation, right? So I was wondering, although they both depend on the line widths and the light matter coupling, is it possible the cooperativities involve different line widths than the light matter coupling, so that's why you get a lot of this variation?
No, I mean, they all involve the same line width. It's that there's a different, they involve a different combination of the line widths, right? So the strong coupling is basically when the Rabi oscillation frequency is higher than the damping rates inside the system, right? And it's just a linear combination of those damping rates. The cooperativity, depends on the ratio of, well, it's basically the ratio of the coupling strength to each one of the line widths multiplied together, right? So instead of having this linear combination, you basically have a product of the 2 of them. And so the emitter line width actually enters much more importantly in the cooperativity than it does in the strong coupling regime. So it's really just that difference that allows you to have, for example, this regime where you have relatively high cooperativity but not have strong coupling. And the plasmonic systems, they have a different set of parameters than, say, the cavities do. The cavities tend to have very small cavity line widths, but then, thermally broadened emitter line widths. We're in the kind of the opposite regime here, where the sort of bad cavity regime, in the plasmonic case instead of the good cavity regime that's typical of photonic cavities.
Okay, so the fact that for the EIT you measure it with scattering, but for the strong coupling you use photoluminescence, I guess that doesn't change the line widths involved and stuff like that.
So the induced transparency doesn't show up in photoluminescence. Again, waving my hands is because of an interference between the radiation produced in a sense between the plasma and the exophthalmic. It's a coherent effect that shows up in scattering because scattering is a coherent process. Photoluminescence is not a coherent process, right? You excite at a certain wavelength and then it relaxes internally and then emits light. So the coherence of your driving field is lost in the photoluminescence process. So the induced transparency comes because of the coherence between the driving field and the scattered field, so you don't see it in photoluminescence. So that's why I like to use photoluminescence as a sign of strong coupling. If you see splitting in photoluminescence, you know you have strong.
Okay, thank you.
Sure.
Okay, next question.
Hi.
So,
I have a question about when you said that when you place the quantum dots on a metal surface and then you take the STM tip, you mentioned that the transition dipole moment of the quantum dots are randomly oriented. This may be a naive question, but if they are spherical quantum dots, what gives them transition dipole moments that are oriented randomly? I thought it should be.
no, that's a good question. So the quantum dots are quasi-spherical, but the underlying crystal lattice is not symmetric. So they have a zinc band crystal axis, which has a preferred crystallographic orientation. So
Okay.
the transition dipole moments, I think, are believed to be oriented perpendicular to the c-axis of the
Okay.
crystal. So it's really the crystallographic orientation of the quantum dots that determines their
Okay.
dipole moments. Sure.
Thank you.
Sure.
Okay, next question.
Hi, sorry, let me ask you one more question. This was a very nice talk. With respect to the ultra-strong coupling regime with a single vibrational mode in a molecule, those theoretical calculations that you were showing at the end, my question is that your motivation is that presumably that ultra-strong light matter coupling will create enhancement of nonlinearities. So what would the ultra-strong coupling regime give you that the strong coupling regime does not in that particular case?
All right, so to clarify, this ultra-strong coupling it was a collective one, and this is experimental data, not theoretical data.
Okay,
the achieving it at the single vibrational level is a vision. I don't think we would achieve ultra-strong coupling at the level of a single vibrational quantum. I mean, the transition dipoles for vibrations are much weaker than electronic transitions. But I think we could reach the strong coupling regime there. For the second part, what does ultra-strong coupling give you that strong coupling doesn't? That's a good question. Right, there have been a number of predictions of exotic phenomena, creating photons out of the vacuum, dynamic Casimir effects, and some of these things have been observed experimentally in superconducting qubit type of systems. I don't know that it's necessarily realistic to get the same phenomena in these sorts of systems. In general, when you reach the ultra-strong coupling regime, the rotating wave approximation breaks down, right? So you get phenomena that come from these counter-rotating wave terms that are qualitatively different from the phenomena that you get in the strong coupling regime. What we could hope to see exactly and what they would be good for, I mean, if anybody in the audience wants to tell me what we should be looking for. Honestly, I would be very much happy to know what the you know, what we can.
We try to look for those effects, but then on a per molecule basis, in the collective regime, on a per molecule basis, we realized that those effects were really small.
Right.
And these dynamical Casimir effects, I mean, you need to do things that are very drastic to just release a few photons per many molecules and things like that.
Right.
So, I mean, I'm not sure how interesting that is in that context.
No, I agree. And you know, the back of the envelope calculations were not very encouraging, I have to say, for that particular effect. But so I can't tell you I have a killer app that opens up in the ultra strong coupling regime. In some sense, it's just even stronger coupling. So all of the effects you get in strong coupling will be even greater than they will be in the strong coupling regime. But
I guess if you can do this in the single particle or single molecule regime, that is interesting. And I was wondering, so you are doing this with phonons, I guess. If you do it with quantum dots, do you think you can do it in a single quantum dot regime?
The ultra strong coupling.
Right.
So if we were coupling to the, I don't think we can get the mode volume small enough with a quantum dot to get into the small ultra strong coupling regime for a single electronic transition inside the quantum dot. You can get smaller mode volumes in a you know, if you're putting a molecule into your gap cavity, because the gap can be that much smaller. And then, you know, the ratio of the mode volume to wavelengths gets smaller if you move into the infrared regime and you're coupling to vibrational transitions. So, you know, what's actually going to be, you know, you can do a highly optimistic calculation and say, yes, I can get into the ultra strong coupling regime with a single molecule inside a gap nanocavity. But you know, are we ever actually going to be able to get there? I'm not sure.
Thank you very much.
Sure.
Okay, maybe we only have time for one more question from Stefan, and for the rest, maybe you can type your questions in the Q&A, and I will send it to our speaker later.
Hello. I just have a question regarding the nanoparticle on the mirror with a single quantum emitter where you don't make it to see a strong coupling. In a series of papers by Jeremy Baumberg and co-authors, they have shown that in that configuration, the coupling of the emitter with the cavity was actually modulated by the degradation of the quantum dot with time. So of the nanoparticle. So right. When they excite the cavity with the laser, it alters the shape of the nanoparticles, and that they show that can enhance the coupling and lead to the strong coupling regime. So did you observe such effect?
So yeah, that's, you know, we actually observed the opposite effect. So this slide here, I didn't go into this in the actual talk, but these two graphs on the left and the right are from the same coupled quantum dot emitter system. So what we did is first measured the photoluminescent spectrum and the scattering spectrum. And then we took a laser and we shot a bright laser and we put it on to the system for, I think it was 30 seconds or something like that. And then we got the spectrum on the right. So you can see there's been a shift in both the quantum dot emission spectrum and in the plasmon frequency. Okay. So the quantum dot, I think, has been slightly photooxidized, and then the metal nanoparticle has been reshaped a little bit. In this case, that actually served to reduce. Well, actually, no. If I look at the graph, it's a little bit higher. Their coupling strength. It didn't give a significant change in the coupling strength in this case. I think in the molecular case, the mode volumes are that much smaller, and they're going to be that much more sensitive to the motion of a small number of gold atoms on the surface. That you'll see more dramatic effects there because of this laser-induced reshaping.
All right. Sure. Okay. Thanks.
Yep.
Okay, thank you. So due to time limit, we'll put an end to today's webinar. Thank you, Professor Pelton. It's a very interesting talk. So maybe I could start to share my screen about the send off.
Yeah, let me try to stop sharing this. I can't stop.
Oh, that's fine. I can directly.
Oh,
Okay,
there you go.
Thank you. Okay, for our next webinars, we'll have Professor Andrew Masser from Cornell University. Don't forget to register using the link, and also it's still on Wednesday, 9 a.m. Pacific Standard Time. And thank you all for joining us today, and thank you, Professor Pelton, and let's meet next Wednesday. Thank you. Bye.